So far we've talked about human perception, right? Our ability to perceive stimuli visually, orally, tactily. We're usually using this type of information and stimuli to help us make decisions and to operate in the world around us. As an orthopedic, for example, we might be responsible for looking at an x-ray like this to determine if we've identified a fracture or if it's just some kind of interference in the image. Or maybe we're searching for our car at night in a dark parking lot and looking for the red one, but it's hard to tell in the dark. And hopefully we're getting there fast because honestly, this parking lot's pretty sketch. Or maybe our job is just to inspect ball bearings as they come off the line, looking for any defects or abnormalities in order to ensure the quality of the entire batch. Industrial quality control is a regular search task performed by human operators. Their main job is to search product for evidence of defects. And hopefully they're able to capture 100% of the defects 100% of the time. But the reality is that, humans are just not that good. We already know that our visual system is a robust system, but it's flawed. We're subject to failures in certain conditions. But when an operator misses poor stitching in a textile product, the product leaves the factory and hits the market. Worst case, BMW gets a snag in the floorboard carpeting, or my t-shirt is off color. But what happens when an aircraft technician misses a sign of corrosion in a turbine that he's inspecting as part of the 100-hour quality inspection? Actually, as part of my graduate research, we looked at this exact issue, and my job was to help design virtual reality training systems to help technicians like this guy practice inspection techniques in a virtual world before hitting the real thing. So, signal detection theory is a method and approach to understanding and quantifying the probabilities that an operator like this will create an error, that he'll miss a sign of corrosion, right? Or that he'll pull a turbine offline because he thinks he spotted corrosion, but it was really just dirt, costing the company then hundreds of thousands of dollars in a grounded engine. Signal detection theory is a way to quantify the ability to distinguish between stimuli and noise. Okay, so let's take a look at how to do it. So as we said, signal detection theory is a quantitative approach that you can use to help understand people's decision-making behavior. It applies to how people detect certain information. The goal of signal detection theory is to estimate two main parameters from past or from experimental data. And the first parameter, called sensitivity, indicates the strength of the signal relative to the noise. The second parameter, called the response bias, reflects the strategy of the response of the participant. For example, the tendency of saying yes rather than saying no. A good example of this is cancer detection by an oncologist. So if you were to visit the doctor and be screened for an abnormality, you'd want the oncologist to correctly detect the tumor in your body. The oncologist must decide if what he sees is in fact a tumor or if it's just noise. And assuming you are an oncologist that has performed this procedure hundreds of times, you might have a track record for correctly detecting such tumors. If there's 100% possibility that the tumor exists, he's going to detect it. But often, the probability of occurrence is not 100%. Even if the probability of a tumor is low, however, your doctor will detect it if it exists. And over time, this performance results in what's known as a bell curve or a normal distribution. And from an analytical side, this is very useful as the normal distribution contains certain mathematical properties which allow us to better understand the decision maker's tendencies. On the other hand, your doctor could correctly determine that in fact no tumor is present and you are free of cancer. And similarly, your doctor has probably made this decision hundreds of times, and these events also follow the normal distribution. Okay, so now we have the probability of two events. The first event would be that the oncologist correctly detects a tumor, and the second event would be that the oncologist correctly decides that no tumor is present. Right, so let's put these events into a table. So the columns here represent reality or the actual stimulus. We can have a true signal, in this case, a tumor, or we can have noise, which may be something that just, looks like a tumor on the x-ray, like a blob or something. The rows then represent the doctor's decision or response. He may decide that there is, in fact, a signal or a tumor, or he may decide that that blob on the x-ray is just noise. And as you can see, if the oncologist correctly detects a tumor, he decides that there is a signal when in fact there truly is a signal present. Also, if the oncologist correctly decides that there's no tumor present, he's determined that the x-ray showed noise when in fact it was really just noise. Okay, so when the doctor correctly detects a tumor, we'll call it a hit. And when the doctor correctly determines that no tumor is present, we'll call it a correct reject. So let's assume that our doctor is fairly sensitive to distinguishing between signals and noise. And when he makes a decision, it falls here on our graph. At this point, we can begin to deduce some information about how our doctor makes decisions. So let's call this A. It's where the black curve, so no tumors, intersects our decision line. And let's call the height of where the green curve intersects our decision line B. So the ratio of B over A is known as the doctor's response bias, and it's denoted by the symbol beta. The response bias is an indicator of just how risky our doctor is. To the right-hand side of the decision line, the doctor will say that he's found a tumor. And to the left of the decision line, the doctor will say that he did not find a tumor. The red area under the green curve to the left of the decision line is known as a miss. This means that the oncologist decides that no tumor is present when in fact there is a tumor present. The blue area under the black curve to the right of the decision line is known as a false alarm. And this means that the oncologist detects a tumor when in fact there's really no tumor. As the decision line shifts from or to the right, the blue area or the false alarm area will get smaller. And likewise, the green area or the correct hit area will also get smaller. And as the decision line shifts to the left, the red area or the miss area will get smaller and the green area or the hit area will get larger. So if this were your doctor, where would you like his decision to be? Would you rather him make less hits, but also have less false alarms? Or would you rather him make less misses, but also have more false alarms? Now let's say that the distinction between tumors and noise is much more obvious. Perhaps the doctor moved from using an ambiguous x-ray to a more certain method like a PET scan, which highlights cancer cells throughout a radioactive tagging process. Then the overlap between detecting a signal and the noise is much less, in which case the normal distributions for determining signals and noise would be spread further apart. And this increases our sensitivity, denoted as D prime. So if we were to place our decision line in the same place as before, we can now see that the red area or that miss area has been reduced and the hit area has been increased. So let's consider signal detection theory in another context and practice how we can derive numerical probabilities from this theory. So SDT is very applicable in aviation inspection, as I mentioned. Aircraft maintenance technicians spend huge amounts of time looking over each square inch of an operational aircraft just to ensure that it's free of defects. Defects that could potentially cause severe consequences during flight. So look at the SDT table to the left. Again, we have the actual stimulus presented in the columns. A signal would constitute an actual defect, such as corrosion, whereas noise would constitute a more non-severe abnormality, which only looked like a defect, like encrusted dirt or something. The rows signify the inspector's decision. This inspector made a total of 400 decisions during his work week. And during 160 of these decisions, he identified a defect when in fact there was a defect. For 40 of these decisions, he determined that it was just noise and when it was really a defect. And he identified 4 defects that were really only noise. But he correctly identified noise 196 times. So now let's look at how we can derive probabilities from these numbers. The probability of a signal was that a signal was present in the aircraft was 50%. And this was calculated from the 200 signals that were actually present divided by the total number of decisions made, which was 400. Likewise, the probability that noise was present in the aircraft is also 50%. And this is derived from the 200 noise abnormalities that were actually present divided by the total number of decisions made. The probability that the inspector would detect a defect, given that the defect was actually present or make a hit, is 80%. And this was derived by dividing the number of hits made, which was 160, by the total number of actual defects present, which was 200. The probability that the inspector would miss or detect noise, given that the defect was actually present, is 20%. And this was calculated by dividing the number of misses made, which was 40, by the number of actual defects present, which was 200. The probability that the inspector would make a false alarm or detect a signal when it was really only noise is just 2%. And this was derived by dividing the number of false alarms made by the total number of noise abnormalities which were present. And then finally, the probability that the inspector would make a correct reject is 98%. And this was derived by dividing the number of correct rejects made by the total number of noise abnormalities which were present. The probability that the inspector would detect a defect, given that the defect was actually present or make a hit, is 80%. And this was calculated by dividing the number of hits made, which was 160, by the total number of actual defects present, which was 200. The probability that the inspector would miss or detect noise, given that a defect was actually present, is 20%. And this was calculated by dividing the number of misses made, which was 40, by the total number of actual defects present, which was 200. The probability that the inspector would make a false alarm or detect a signal when it was really only noise is 2%. And this was derived by dividing the number of false alarms made by the total number of noise abnormalities which were present. Finally, the probability that the inspector would make a correct reject is 98%. And this was calculated by dividing the number of correct rejects made by the total number of noise abnormalities which were present. So how do these numbers compare to the normal distributions we've been working with? Here you can see that the green area under the curve is 80% and signifies the probability of making a hit. Similarly, the red area under the curve is 20% and signifies the probability of missing a defect. Again, imagine how moving the curves farther apart would impact the inspector's decision sensitivity. And also imagine how moving the decision line from the response bias would affect the probability of making hits and misses.